All right, so just a reminder that today's material is going on exam 2, right? It's not going to be on this Thursday's test. It will not be on exam 1. This will be on exam 2. So if you're keeping track of your notes, and actually the stuff we talked about on Friday is on exam 2 as well. All right, so we're going to talk about phase changes today. Specifically, we're going to talk about factors influencing the phase change between liquid and gas. So when we boil a liquid, right? What happens there? I take some water, I put it on over my Bunsen burner, I heat it, and then I stare at it, and then it boils. What is happening? Going from the liquid phase to the gas phase, right? H2O liquid becoming H2O gas. If I asked you, what's in the bubbles? Your answer would be H2O, right? It's liquid phase going to the gas phase. This is a physical change. I have students tell me all the time that that's chemical change, and you always lose points for that, right? Because you have not broken bonds. You're just changing states, changing from the liquid state to the gas phase. If I took it from the liquid phase and I froze it, that wouldn't be a chemical change either, right? That would be a physical change. So just keep in mind to yourself that boiling, which we typically call vaporization, because boiling is actually an equilibrium. We'll talk specifically about what boiling means a few lectures from now. But vaporization is the word we use to refer to going from liquid to gas. And so particles in the liquid are close together, right? Particles in the gas are far apart. I mean, this is all stuff you learned in like elementary school, but it's always good to remember phase changes are physical change. Physical change, physical change, physical change. All right, so the process of vaporization, if you could see it at the interface of your level of liquid, right? You've got particles in the liquid phase going to the gas phase, right? This process is called vaporization. And so when we talk about boiling, boiling is something specific, right? Boiling is an equilibrium between liquid and gas. So that's why we can't call all phase changes involving liquids becoming gases boiling, because vaporization occurs even when it's not boiling, right? If I dump out my water bottle and walk away for 5 hours and come back, my liquid will be gone, right? And I didn't boil it, I vaporized it. So just make sure you understand the difference there. These particles in the liquid phase are becoming to the gas phase. And then a small number of them are going back down to the liquid phase as well, depending on the temperature especially. All right, so we're going to be talking about intermolecular forces, which I refer to as IMFs for short. And I've given you a little handout. This is just the chart, so you don't have to spend so much time writing. For you to fill in as we're going through this stuff. This is a subject that a lot of students struggle with. Actually, the subject of my doctoral dissertation was, how well do students learn intermolecular forces? So, spent a lot of time studying how students know and understand intermolecular forces. All right, so what are intermolecular forces and what are they not? It's so important that you understand what the definition is. Okay, IMFs are not chemical bonds. They are not bonds, okay? Remember, a bond involves sharing of electrons or transferring of electrons, cation, anion situation, right? That is not what we're talking about when we're talking about intermolecular forces. Okay, think about it like a magnet. Even if you get two really strong magnets, you put the positive end of one and the negative end of the other together, they stick, right? Is that a chemical bond? Magnets sticking to each other, is that a chemical bond? No, right? Okay. You can think about intermolecular forces as like little atoms sticking together like magnets. Okay, you can think about atoms as teeny tiny little magnets on the atomic scale sticking together. Okay, just always think back to your refrigerator. If you have magnets on your fridge, I've got a ton of magnets on my fridge, right? When I put that magnet on the refrigerator, there's no bond, right? That's not a chemical bond. My 4-year-old walks by and pulls it off with no effort, right? That's not a chemical bond, okay? Intermolecular forces are not covalent bonds. They are not covalent bonds, okay? So these are attractions that occur in between. That's hence the word inter, okay? Inter means in between, okay? In between. So the significance here is that they are weaker than chemical bonds. Now, I have to put an asterisk next to that because there are some intermolecular forces that can be very strong. But in terms of magnitude, okay, they're not the same as a chemical bond. So a chemical bond is called an intramolecular force, whereas a intermolecular force, ER, is in between molecules. Intramolecular occurs within the same molecule. So here's a picture that represents that, right? A covalent bond would be an intra with an A, intramolecular force, right? That's a covalent bond. That's a pair of electrons being shared, right? Whereas this is an intermolecular force. We represent covalent bonds with a solid line. We represent IMFs with dashed lines, okay? So that you can tell one's an attraction, one is a bond. There's a big difference here, so we have to represent that, okay? This is an intermolecular attraction. Specifically, it's a dipole-dipole attraction, right? Because this is a negative end, this is a positive end. So we'll talk about that today. But first, we have to establish the baseline. What is an intermolecular force and what is it not? It is not a bond. Okay? There's not a bond between this chlorine and this hydrogen, right? These two atoms are not bonded to each other. They are attracted to each other. Just like if I take the negative end of my magnet, put it near the positive end of another magnet, and they click together, right? That's an attraction. That's not a bond. Same thing here. We use the dashed lines to represent IMFs. We use solid lines to represent chemical bonds. All right, so these are the types of intermolecular forces. They're all listed on your handout. We're going to go through each one of them, okay? Now, just so you know, I put that little box there for strength. I'm not going to make you memorize, you know, the values of the strengths. It's just there for you to have a frame of reference, okay? So you don't have to worry about, oh my goodness, do I need to memorize that as 0.05 to 40, right? You don't need to memorize that. You just need to know, in terms of ranking, where they stand up to each other. So the first one we're talking about is dipole-dipole. Dipole-dipole. We used this word on Friday. What is a dipole? By definition, what's the definition of a dipole? A molecule that is polar, right? Any molecule that is polar, okay? Because we talked about dipole moment, right? And we said we calculate dipole moment to figure out quantitatively how polar a molecule is. So dipole-dipole intermolecular forces occur between polar molecules. So any polar molecule will exhibit dipole-dipole forces. So I'm going to give you some examples. Again, don't obsess about calling them, you know, memorizing this number. And just so you know, these are collectively referred to as van der Waals forces. Okay? If you ever see van der Waals forces in a book, that's what it's referring to, intermolecular forces, and van der Waals forces are one and the same. Okay, so any polar molecule is called a dipole. I just said that. Right? So any polar molecule that you see, if I give you a molecule and say, what IMFs are in this, you look at it and decide, hey, this is a polar molecule. You need to list dipole-dipole will be as one of its IMFs. So any polar molecule is going to exhibit this. So think about it just like a magnet, right? It's going to be, the positive end will be attracted to the negative end, the positive end will be attracted to the negative end. Two negatives would obviously repulse each other, right? Two positives would obviously repulse each other. So positive attracts to negative, negative attracts to positive, right? Just think about it like a teeny tiny little magnet, because that's essentially how we should think about it. A polar molecule has a positive end and a negative end. A magnet has a positive end and a negative end, right? You probably grew up playing with magnets, seeing how the positives and the negatives attract to each other. So these are present in polar molecules. So if you are looking at a molecule and you're deciding, okay, what intermolecular forces will be present in this molecule, and you see that it's a polar molecule, then you should definitely write dipole-dipole, okay? Because all polar molecules will have this intermolecular force. And so here are three substances, all right? I've given you their molar masses, I've given you their boiling points, and then I've given you dipole moment. So of these three, which one of these is most polar? This one, right? This one's got the highest dipole moment. This has got the highest boiling point. All right, we'll talk about the relationship between intermolecular forces and boiling point in just a minute, but we can go ahead and preview it now. Right? If those molecules in the liquid phase are sticking to each other very intensely, it would take a lot of energy in to overcome that sticking. Right? So if they're sticking to each other, like little tiny magnets, right? I've got weak magnets versus strong magnets. It takes more effort to pull apart strong magnets versus the weak ones. This one's the most polar. It's got the strongest intermolecular forces of the three. It's got the highest boiling point. Now, this you need to know, okay, when we're going to be looking at several molecules in this discussion with a C double bond O, which is called the carbonyl carbon. Okay, you'll see this word a lot when you take organic chemistry. You're going to spend a lot of time talking about the reactivity of this functional group right there, a lot. A carbonyl carbon is capable of dipole-dipole. So even if the rest of the molecule is non-polar, but you've got a carbonyl, okay, that little tiny region you can think of as a little tiny dipole, right? This will be your partial negative, this will be your partial positive. Okay, so just make note that a carbonyl carbon, which is a C double bonded to an O, okay, and there are two lone pairs right here, would be capable of dipole-dipole forces. You're going to see lots of molecules containing the carbonyl. Obviously, we're not going to do the organic chemistry side of it and do the reactions. We're just going to identify the intermolecular forces. Everybody with me so far? Does everybody understand dipole-dipole? I start with that one because we just talked about dipole moment on Friday. Right? So it makes sense that we start with where we left off. All right, let's do London forces or London dispersion forces. Okay, now the range here is 0.05 to 40. You don't have to memorize that value. What you do need to know is what I put this little asterisk. The strength varies by structure. That's a big range, right? 0.05 to 40 is a big range. Why is that? The strength of London dispersion forces is a direct result of the structure, of the Lewis structure of that molecule. Specifically, we're looking at, we're looking at the three-dimensional shape too, but we're also looking at the length of the chain, how the chain's put together. Okay, so this all comes from structure. So what happens? Where do I find London dispersion forces? They are present in all molecules. I should say in all atoms too, because it's not just all molecules, it's all atoms. And the strength of London dispersion forces depends on the size and on polarizability. I know that is a $20 word. We'll talk about what it means in just a second. I'll give you a second to jot this down. So you can call them London forces or you can call them London dispersion. They mean the same thing. So all atoms have London forces. Every single atom has London forces, okay? And then by that logic, if every atom has it, then obviously all molecules would have it too. So if I give you any substance, any atom, and say, what are the IMFs? The first one you should obviously list is London forces, because everybody's going to have London forces. Will everybody have dipole-dipole? No, everybody will not have dipole-dipole, right? So if I give you a polar molecule and say, list off the IMFs, you would obviously say London first and then dipole-dipole. If it's not a polar molecule, then you wouldn't list dipole-dipole. So let's talk about what London forces are. So we're going to pick, you can pick any atom. This is a figure from your book. A helium atom. Let's just pick a helium. That's a really simple atom, right? 2 protons, 2 electrons, right? In terms of the charge, 2 protons, 2 electrons. Yes, we agree. Now, we haven't talked about the quantum model yet, but you know from your past experiences in science that these electrons are moving out here, right? And they're moving freely. We've already talked about why. It's not the Bohr model. We haven't gotten to the nitty-gritties of the quantum model yet, but you do know that these electrons are moving out here randomly, independently of each other, right? We call that the electron cloud. This electron's moving independently of this electron. So just think about it from a simple probability standpoint. Probability-wise, is it possible for a split second in time that both electrons are on the same side of the atom? If they're both moving independently of each other, is it possible from a probability standpoint that they both end up on the same side? Of course, right? And so for that split second, okay? For that instant, your molecule would look like this. It would be partially negative on one side and partially positive on the other side, right? For that instant only, because these two electrons just happen by chance to end up on the same side. Two electrons are negative. There's no charge over here, right? So this side would have high electron density. This side would have 0 electron density. So it would actually look like this. It'd be partially negative and partially positive. Now, is it going to stay that way forever? No, it's going to be that way for a second, for a split second, right? But for that particular instant, this is actually, you could think of like a little dipole for that split second. Now let's just pretend that there was another helium atom nearby. Its orientation was slightly different, right? For that split second, could the one that was polar, quote unquote, be attracted to the one that would be, slightly oriented in a different polarity, right? They could, right? They could. For that split second, they would be attracted to each other. And so these are instantaneous attractions. This is what you need to know right here, this second bullet. Actually, the third one too. London dispersion forces are instantaneous attractions due to the movement of electrons. All atoms, all molecules have London forces. Every single one of them. Every single one of them. They're instantaneous, okay? That's the key word. Bold, underlined. They're instantaneous. They're short-lived. Very, 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 very short period of time that these IMFs are sticking around. Now, if you're talking about a tiny little atom exhibiting one intermolecular force, that's not the same as a humongous molecule. Okay? That's why I say that the influence of London forces varies by structure. And I'm going to show you more examples, but I try not to talk too much while you're writing. Does everybody understand the theory of London dispersion forces? They're instantaneous. They're based on the motion of electrons. Does this make sense? Yes, yes, yes. So when we're doing this intermolecular forces business, there's no math. We're not going to be doing any calculations with it. Which is why it's so important that you understand the theory, right? Because there's no math to save you if you don't know how to do the theory and explain the theory. You can be like, I can at least do the formula, right? You don't have any math to fall back on this. It's all theory, no math. So make sure that if this isn't making sense, we get it cleared up. Everybody good on what London forces are? Okay, so this is a figure from your textbook, right? So far apart, they're not influencing each other very much. There is a function of space, physical proximity, right? If one's 50 feet away from the other, there's not going to be, that instantaneous dipole isn't going to influence another one. But when they're close enough, like say in the liquid phase, this is where we see these effects, right? So if you've just got one atom experiencing it, who cares? But if all of them are experiencing this, even if it's for split seconds, right, this could add up. Do you see how this could add up quickly? And so, again, all atoms, all molecules will have London forces. Now, here's the scenario where you'll have London forces only and nothing else. If you have a nonpolar molecule, obviously you can't have dipole-dipole. So you would list London forces only. If you have a hydrocarbon, so that means it's a molecule with a CXHY with no modifications. So that means there are no functional groups, there are no carbonyl carbons, there are no amino groups, etc. Or if it's just a single atom, right? If I said, give me a list of all the IMFs in xenon. Xenon's a single atom. The only IMF it would be capable of would be London forces. So these are the scenarios where London is the only thing you're going to list. Nonpolar molecules, hydrocarbons that are not in any way modified, or monatomic atoms, or even a diatomic, right? F2. That's going to be a nonpolar molecule. That would fall in the nonpolar category too. All right, so let's talk about that word I used a second ago, polarizability. What does that mean? The definition of polarizability is the ability of an atom to have an instantaneous dipole, right? An instantaneous dipole is that split second where it's partially positive on one side, partially negative on the other side for that trillionth of a second. Now, the larger the atom, the higher the probability of having those instantaneous dipoles is. Think about why. The more electrons you throw into the party, the higher the probability you have of getting an instantaneous dipole. So if we're comparing lithium versus uranium, right? Both of these are single atoms, right? Lithium has 3 electrons, whereas uranium has 92 electrons. So if I said, which atom is going to have stronger London forces, your answer would be uranium, right? 92 electrons versus 3. The more electrons you have in the party, the higher the probability of you have those split-second dipoles. Okay, so polarizability just refers to the ability of the atom to get those split-second attractions. Right? More electrons equals greater probability. So that's what polarizability means. That's why I say the net effect of London forces comes from size and polarizability and structure. We'll look at the structural effect in just a second. All right, now let's look at polarizability and molecular size. The larger the molecule is, okay, the higher the probability of having those instantaneous dipoles goes up as well. I mean, this makes sense, right? Because this is methane. Does anyone know what a 6-carbon chain is called? Anyone remember? Anyone have to learn that in high school? You know what the prefix for 6 is, though. What's the prefix for 6? Hex, right? This is hexane, this is methane, right? So this is a 6-carbon chain, it's a linear carbon chain. All 6 carbons are in a row, right? With hydrogens on each one of them. So a 6-carbon chain versus a 1-carbon chain, okay? So the effect of these London forces is significantly higher in hexane than it is in methane. Okay? Hexane is a liquid at room temperature because of this, right? This chain, long linear chain, versus single chain of 1, right? That's a carbon with 4 hydrogens on it. They're both nonpolar, right? So they both only have London forces as their intermolecular force. Why is it so much greater in this one? Because it's a long chain. Okay, so think about overcoming intermolecular forces like pulling apart magnets. You can think about it like that. Or you can think about it like pulling apart pieces of Velcro. Okay? If you've got a piece of Velcro that's this long versus a piece of Velcro that's this long, right? Which one are you going to have to put more effort to pull apart? Right? If these are all stacked on top of each other, which is how it would be, right? Because this is a linear molecule. Stacked on top of each other, nice and neat. You have the instantaneous attractions going all down the line versus here, you don't have that same effect. All right, so long linear molecules will have stronger London forces than, say, a short, fat molecule. And I know this is a hard way to represent it, so I'm going to sketch it on the board for you. Hopefully the video doesn't freak out when I write on the board like it used to. All right, so this is pentane, and this is a structural isomer of pentane. So this is C5H12. 1, 2, 3, 4, 5. I wrote in the wrong spot because I need to have room for my hydrogens. We'll write it off to the side here. All right, there's the Lewis structure, oops, for pentane, linear, okay? Now this one also has the formula C5H12. But look at how it's put together. Okay, what's the difference? These are both C5H12, right? They're called structural isomers. That means they have the same chemical formula, different connectivity. So they have different names. And this one's linear. This one you could think of as like a T shape. All right, if you have linear versus, let's just say T shape, these are all going to stack on top of each other. They're capable of stacking on top of each other. Right? And so you have the capability of polarizability all down the chain. The whole way through, right? Everywhere where there are atoms in each other's proximity, you have the possibility of those London forces, right? Versus in the one that looks like a plus sign, right? They're not going to stack on each other nice and neat. So you'll have attractions in a way that is not the same intensity. Does this make sense? Does this make sense? Okay. There's greater surface area between you, right? So in other words, you have all down the line, you've got the chance for these London forces. Versus here, you've got it at certain points. I mean, and it'd be possible here and here too. I'm just trying to simplify it, right? They're not touching each other as much. Does this make sense? This is why structure strongly influences London forces, okay? The structure is the big, big influence here. The greater amount of touching there is, the greater the probability of instantaneous dipoles, anyway, because it's a long molecule, and the greater the effect of that, okay? They're closer to each other, and they are on top of each other, right? So it'd be like pulling apart a big piece of Velcro. Does this make sense? Yes, yes, yes. Okay. So the longer the chain is, the stronger the London forces are as well, right? So it has an influence on chain length as well. Here's some data. Okay, all of these ones are gases at room temperature. All of these ones are liquids at room temperature, and all of these are solids at room temperature, right? This is a 20 carbon chain. This is a 30 carbon chain. These are all, that's 5, 6, 7, 8, 9, 10, 11, 12, right? And then here's 1 through 4 carbon chains, right? They're all gases at room temperature. All of these have only London forces. If I said, what's the intermolecular force in all of these, your answer would be London forces only, right? Because they're all nonpolar. These are all hydrocarbons that are in no way modified. They're nonpolar, right? Because remember, the electronegativity of carbon and hydrogen is the same. Well, its electronegativity is 0.4, which we still classify as nonpolar. So these are all nonpolar, so the only influence here is London forces. So why is the London force so greater down here versus up here? Well, this is a 20 carbon chain and a 30 carbon chain versus a 12 carbon chain. Okay, let's move on to ion dipole. 10 to 50 is the range we're going with. You don't have to memorize that value. This occurs between ions and polar molecules. It's the name ion dipole. And this is what allows ionic substances to dissolve in water, for instance. When I take NaCl solid and I dump it in water and I stir, 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 right? That's what's allowing this to occur. All right, so here's an example of ion-dipole interaction. We've already established that water is a polar molecule, right? We talked about that on Friday. Talked about why water is a polar molecule. So there's a large partial negative here, and there's partial positive, partial positive. This is a cation, right? So it's very positive. This right here is the ion-dipole intermolecular force. Now, it's not in reality a 1-to-1 ratio. Okay, what it looks like in reality is they're surrounding the water molecule. We're going to talk about this in great detail when we talk about the solution state. But I just want you to understand. The waters for the cations are facing inward, right? This is the oxygen atom. They're all facing in the cation. Look at the anion. What's happening here? Is the water, the oxygen sticking in? It's the hydrogen, right? Hydrogen's facing in the anion. And so this process is what's allowing for solution formation. And when we talk about dissolving an ionic substance in water, it's because of this ion-dipole intermolecular force. And this will play a big role in solution formation, and we'll come back to it in greater detail when we talk about solution chemistry, but I want to introduce it now while we're talking about IMFs. Okay? And then the last one is called hydrogen bonding. Hydrogen bonding. It occurs in molecules containing OH, NH, and FH bonds. OH, NH, FH. Now, don't let the name throw you off. Are intermolecular forces covalent bonds or ionic bonds? No, they're not. What are they? They're not bonds. What are they? IMFs are what, though? They're attractions, right? They're attractions. So here is the deal on hydrogen bonding. So hydrogen bonding is just a special type of dipole-dipole. It's a special condition. It's like a subcategory of dipole-dipole. Because what happens is when you've got a hydrogen bonded to a nitrogen, think about the electronegativity difference there. Nitrogen, pretty electronegative. Hydrogen, 2.1. Right? It's not anything to get super excited about. Versus hydrogen bonding to oxygen. So this one's 3, this one's 3.5, this one's 4. Right? This is 2.1. So it's going to get a pretty polar bond there, right? It's going to be a pretty significantly polar bond. And so the dipole-dipole interactions it'll have are pretty significant. And so any molecule that has HF, HN, or HO bonds will have hydrogen bonding as an IMF. Now, if I gave you water, for instance, and I said, okay, list the intermolecular forces in water, you would not list dipole-dipole because it has hydrogen bonding, okay? So you don't list both dipole-dipole and hydrogen bonding unless there are places in the molecule where dipole-dipole exists and places in the molecule where hydrogen bonding exists. If it's just straight up water, okay, you're only going to have London forces and hydrogen bonding. So I'm going to show you lots of examples of this. We're going to practice it too. Right? All of these would have hydrogen bonding. You would not list dipole-dipole. While you're jotting this down before I forget, on Wednesday, if you have markers, crayons, colored pencils, highlighters, any sort of coloring, you can bring your paints, whatever, we're going to get artistic on Wednesday. We're going to be coloring. So if you have any of that, please bring it because I don't have a whole lot of that kind of thing. All right, so here's hydrogen bonding in water. Again, remember, this dashed line represents an attraction, right? So the positive end is attracted to the negative end. Okay, that's hydrogen bonding. Chemical bond is actually occurring here. This is an attraction. This is a chemical bond. Covalent bonding here, covalent bonding here, attraction here. Here's another picture just showing the same thing. DNA strands are actually held together by hydrogen bonding. Okay. Maybe that's something you talked about when you took biology. Maybe it's not. I don't know. The chain itself, right, each individual chain, those are all covalent bonds. Right? So this chain is all covalent bonds. And this chain is all covalent bonds. But what's holding the two sides to each other, the A and the T and the G and the C, that's actually hydrogen bonding. Okay? And one of the things that I know a lot of textbooks show is like those rungs, right? It represents it as rungs. And that's kind of misleading. right? Because is there a covalent bond here between these pieces? Are those covalent bonds? No, they're attractions, right? And so, again, think back to the fact that when it occurs on a large scale, right, that can add up. So these are not actually covalent bonds. So the two rungs really shouldn't draw it as like a solid line because that's misleading, right? It's not a solid line. You should draw it as a dashed line. This is something I know a lot of textbooks talk about, right, when you take biology. But when you think about it from a chemist's perspective, right, those two strands of DNA are not actually covalently bound to each other. They are held together by hydrogen bonding. All right, so here's a summary of our intermolecular forces that we're talking today. This one's dipole-dipole, right? These are both polar molecules. This is London dispersion. These are two nonpolar molecules. This is ion dipole. There's the cation. There are my anions. And here's hydrogen bonding, right? So for instance, this is important, right? This is methanol, CH3OH. So the hydrogen bonding is not happening on the CH3 part, right? It's only happening at the OH. So when you have a molecule containing hydrogen bonding, keep in mind, it's only occurring at the OH or the NH or the NH2, right? Okay? It's not occurring at the entire molecule. It's only occurring at a specific place. And so when we take it back to boiling, right? I showed you an image a while ago now on the different boiling points as a result of dipole moment. If these intermolecular forces are what's holding the particles in close proximity in the liquid phase, you've got to overcome that to boil it, right? You've got to overcome all those intermolecular attractions in order to boil your liquid, or in order for it to even vaporize, right? Even if you just spill it on the floor and walk away, how long it takes for that spilled liquid to evaporate is going to be a direct result of the intermolecular forces as well. Okay? The stronger the intermolecular forces, the higher the temperature has to be for it to boil, the longer it'll take for it to evaporate. Lower the surface pressure will be, and the vapor pressure will be, right? All of those things come directly from intermolecular forces. Okay? So this is why, knowing in IMFs, you can predict the boiling point. And so here are some boiling points. This is a figure from your textbook. Right? There's methane versus ammonia versus HF versus water. Okay, so one of the things that if I gave these three and these four, and I said, okay, rank these by boiling point, everybody gets the bottom one, and everybody gets methane, lowest, non-polar. Everybody usually gets water, because they know water's got a high boiling point. Here's where students get messed up. And so the thing you have to think about here is a lot of students say, oh, three hydrogens, three hydrogen bonds, right, versus one. The thing you have to consider here, and this is the example we talked about on Friday with the, which one was it? It was CHCl3. Yeah, it's kind of a similar result, right? When you look at the molecular geometry, okay, the dipole moment is less in NH3 than it is in HF. So just keep those kinds of things in mind too. All right, this figure's in your textbook as well. It's table 11.5 if you want to go back and see some examples in your book. These are all the ones we talked about today. So if you want to make a note to table 11.5, that's where this can come from. And this figure's from, I think it's from your book too, right? So you can ask yourself, kind of go through this flow chart and decide which IMF we have. All right, so let's do practice problems because this is something you're going to have to do. And like I said, this is all theory, right? There's no math. So being able to identify intermolecular forces and explain them is very important because there's no calculations. Like you don't have to understand molarity to do a calculation of it, right? You can be like, I don't know anything about molarity, but I know moles over liters. I can do that in my calculator. Well, there are no calculations to save you here. So you need to understand the theory really, really well. Okay, so take a second and think about this. Which one's going to have a higher boiling point, N2 or O2? Take a second and think about it, and then we'll go over it. Pause the recording. Let's go over this one, N2 versus O2. Okay, are either one of these polar? Is N2 a polar molecule? Is N2 a polar molecule? No, right? Is O2 a polar molecule? No, right? So they're both nonpolar, so that means we can rule out dipole-dipole. By definition, if we rule out dipole-dipole, that means that there's no H bonding. And ion dipole would also be out too. So the only option we're left with is got to be London forces only. London forces are the biggest influence on both of these. The only influence on both of these. So who's going to have a higher boiling point? It comes down to what? Size, exactly. So who's bigger, N2 or O2? Molar mass of nitrogen is 14. Molar mass of oxygen is 16. Right? So if you're looking at the temperatures, right, these are both gases at room temperature. 77 Kelvin versus 90 Kelvin, right? They're both gases at room temperature. This one's more polarizable. Larger molecule, greater polarizability. Makes sense? Number of electrons is greater in oxygen than in nitrogen. Questions on this one? Mm-hmm. Or you could look at number of electrons, 8 electrons versus 7. Either way, their final answer is that it's more polarizable. Okay, I've given you molar masses this time just as a gift. Which one's going to have a higher boiling point? I'll pause it and let you think about this one. HCl with a molar mass of 37.5 versus argon with a molar mass of 39.9. Take a second and think about that one. All right, let's go over the answer here. So I gave you the molar masses. Actually, try to throw you off here, right? Who's going to have the higher boiling point? It's not argon by a long shot. Yes, argon's molar mass is higher, but are both of these nonpolar molecules? No, right? Argon's obviously nonpolar. It's monatomic. Is HCl nonpolar? No, that one's polar, right? So, big difference. This is London forces plus dipole-dipole, whereas this one's London forces only. There's a big difference here. Do we understand this answer? So, bottom line is you can't just base it always off of molar mass, right? Unless they're both nonpolar. If they're both nonpolar, then sure, go for it. But even if they're both nonpolar and the same molar mass, you still have to look at how they're put together. Remember the example I showed you with C5H12, right? Both of those would have the exact same molar mass. If one's linear and one's branched, that's going to make a big difference too. Does this one make sense? Okay, who's going to have the higher boiling point here? NH3 or N2O? I'll give you a second to think about that one. All right, let's check this one out. Starting to get a little bit harder, right? Now we're dealing with nitrogen compounds. Both of them are nitrogen compounds. There is a significant winner though. Which one is it? NH3 versus N2O. Anyone brave enough to voice their answer? You think NH3? Okay. Any votes for N2O? Any votes there? Okay, there are the molar masses, if you want to look at the molar mass part. Right? 17 versus 44. Big difference comes from one's capable of hydrogen bonding, one's not. NH3 is the correct answer. Right? NH3 is capable of hydrogen bonding, whereas N2O is only capable of dipole-dipole. So, picking the correct answer, great. Then you need to explain it too. Okay? It all comes back to intermolecular forces, because those are the forces of attraction that are making the molecules stick to each other. By the way, if you write NH3 has more bonds to break, I will mark you wrong. Okay? Because when you boil a liquid, are you breaking bonds? You are not breaking bonds. What are you overcoming? You're not overcoming covalent bonds, you're overcoming intermolecular forces. I mark so many people wrong for this every semester. Okay? Make sure that when you explain your answer that you don't say NH3's got stronger bonds or NH3's got more bonds to break. Okay? because you're not breaking bonds. If you were breaking bonds, then boiling would not be a physical change, right? It would be a chemical change. So please, 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 make sure that your wording is very careful when you describe your answer. Okay, just shout out your answer here. How many, or what IMFs do you have in hexane? C6H14. Your first answer should always be London forces. Is there anything in addition to that? No, right? This is a nonpolar molecule. It's a hydrocarbon. It's not been modified. Yeah.
On that, I think it was N2O.
Mm-hmm.
Why was that polar?
Well, I'll draw the Lewis structure for you in a second. All right, let's get through a couple more of these, and then we'll go back and look at that one. Okay, IMFs in methanol. I think we've actually already talked about this one. There's the Lewis structure. Well, that's not the Lewis structure. That's the space filling model. What IMFs would we have? First answer you always shout out is London forces. Then you ask yourself, is there anything in addition to it? Hydrogen bonding, right, from the OH, right? So this part right here is the OH part, okay? Make sure you understand. This part down here is not participating in any sort of hydrogen bonding. Okay? So the dot, 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 dot would be between this part and the OH of another molecule, not the CH3, okay? Methyl group, that's nonpolar. Okay, van der Waals forces in Greece. London forces, anything beyond that? No. Okay, I'll give you a second. I want you to state the IMFs in each one of these, and then pick the one who has the highest boiling point. Let me pause the recording for just a second. Let's go back through this one. So, intermolecular forces in CH3, which, by the way, is ethane. London forces, anything beyond that? No. Okay, there's methanol again. We just did that. What are the intermolecular forces there? London, hydrogen bonding. And then this one is ethanol. What do we have there? London, hydrogen bonding, right? So we can clearly eliminate ethane, right? Immediately out of the gate, ethane's out the door because it's nonpolar. So we're down between the two that have hydrogen bonding. Which one's going to have the higher boiling point? Methanol or ethanol? Ethanol has a significantly higher boiling point. Why? The chain length, exactly. Right? That extra chain length has a huge impact, humongous impact on boiling point. Questions on this one? Okay, let's go back about the N2O question. All right, so your question was, why is it polar, right? Okay. So this is definitely a good question to ask. All right, so first step in drawing the Lewis structure. N2O, okay, 5 valence electrons times 2, so that's 10 plus 6, that gives me 16. So now we figure out who's the central atom. Who's the central atom? Is it nitrogen or is it oxygen? Nitrogen's got to be the central atom, right? Because it is the least polar, the least electronegative. Okay, so 2, 4, so minus 4, that gives me 12 remaining. 2, 4, 6, 8, 10, 12. Okay, so now I've got a situation on my hands, right? I don't have an octet on my central atom, so what do? Make double bonds, or you could make triple bonds too, right? Let's come up with our options. We could have N single bond, double bonds on both sides. Oops, I did it again. We could have single bonds on both sides, right? We could have a triple bond on this side, and triple bond and single bond O. We could have a triple bond on this side, right? Because it's not like CO2 where you have a triple bond on one side. It's the same as having it on the other. Right? And even in that case, triple bond is less preferred anyway. Let's put it on the side so we can see it better. Okay, so now we have to go through and choose which one is the correct answer. And that comes from formal charge. Okay, so you don't have to go through and calculate it because I've already done it. This one is your winner. This one's your winner because this gives you a formal charge +1, this one's 0, and this one is -1. Okay? You want to have the negative formal charge on the most electronegative atom. So in this Lewis structure, you've got all this electron density here, right? This is a linear molecule, right? If you think about its molecular geometry, this is linear. You've got high electron density here, so you've got this, and that's what makes it a polar molecule, right? You have your going that way. Does that make sense? Okay. All right, so that's where we're going to stop for today. Just a reminder that your first exam is this Thursday.